In this video, we'll be running an ANOVA in RStudio. I'm going to be using our example data set that I've brought in previously and named example in lowercase. And for this video, we're going to be seeing if cholesterol differs based on the exercise group. However, before we get started with that analysis, we're going to subset our data based on a couple of different conditions. Let's say that these participants who enrolled in this study were given an option to do a follow-up study, but they had to meet certain criteria. They either had to have a resting heart rate of under 100 beats per minute or have a diabetic status of no. So let's pull those participants that meet either of those conditions into their own subset. We're going to call our subset my subset and pull the cases from our example data frame where either of our conditions are true. We'll use our square brackets to index the data frame, give it our first condition, which is a resting heart rate of less than 100. Then, because we need either that condition to be true or to have diabetic status be no, we'll use the or symbol, which is the vertical bar. Then we'll give it our second condition. After the end quote for our no label, we'll include a comma to tell R to pull all of the variables from our original data set where either of those conditions are true. We can see in our environment window that 60 out of the 65 participants were able to be included in the follow-up study. If I view my subset, I can see that there are some participants with a resting heart rate of over 100, but notice that they have a no in the diabetic column. There are some that have a diabetic status of yes, but they meet the other condition, having the resting heart rate under 100. So as long as they meet one of those conditions, they are included in this my subset. Now the analysis we want to run on this subset of participants is to look at the cholesterol and see if it differs based on our exercise grouping. So let's visualize this relationship with a box plot. I'll use the box plot function, give it my numeric variable, which is cholesterol, then the tilde symbol to mean as a function of the categorical variable. This will produce a box plot where we see our cholesterol on the y-axis as a function of my never, sometimes, often exercise variable on the x-axis. We can see that those who never exercise tend to have a higher cholesterol than those who sometimes or often exercise. And although there are a few points that are falling away from the distributions in some of these groups, we can see that they're roughly normally distributed and have a fairly constant variance across all groups, which will meet the assumptions of our ANOVA test. Before we run the ANOVA, let's calculate the group means for each of our exercise groups to compare them. To do that, let's subset our data further into 3 different data frames, one for each of my exercise groups. I'll call the first subset never, and I'll pull from my original subset only the cases where exercise is equal to never. We can see the 18 participants from the my subset who never exercise are now in their own data frame, and now I can calculate their mean cholesterol. We can see that the never group has a mean cholesterol of 387.67. I can repeat this for my other 2 exercise groups. With my group means, I can see that the never group has the highest cholesterol, followed by the sometimes group, and finally the often group has the lowest. The ANOVA is going to tell us overall if there are any significant differences among these group means. So let's carry out the ANOVA. First, we'll define a model that tells R what variables will be going in our ANOVA. I'll call it my model. And using the AOV function, I'll use the same notation as I did before, having our numeric variable tilde as a function of our exercise variable. I can use the shorthand data option to provide the name of the data set that those variables belong to. Just to note, I could also use the same exact syntax as I have in my box plot function by using the data frame $ variable name notation. These two expressions are equivalent. Once my model is defined, I'll use the summary function and pass it my model to get the output of my ANOVA. We can see my ANOVA table displayed in the console. Our degrees of freedom for both our exercise factor and our residual error degrees of freedom, their sums of squares, their mean square, and the F statistic of 5.94. The p-value associated with our F statistic is less than our alpha, meaning we would reject the null hypothesis that the mean cholesterol is the same across all three exercise groups. Because we're rejecting the null hypothesis, we know that there's a significant difference in cholesterol somewhere among these groups. To investigate that, we'll run our post hoc analysis using the Tukey HSD function. The Tukey HSD will run our post hoc comparisons using the Tukey adjustment, and we just need to give it our ANOVA model. In the table provided in the output, we see each pair of exercise groups compared. We can see that if we take the mean of our often cholesterol and subtract the never mean, we'll get a difference of 112. We have confidence interval bounds for those differences, and the important part to look at is our adjusted p-value. Again, these p-values are adjusted using the Tukey adjustment, so we just need to compare them to our original alpha level. We can see that our often group significantly differs from our never group, but the other comparisons, sometimes versus never and sometimes versus often, are not significant.